Okay, so we continue now with chapter 5, and we're going to close this chapter with two or more or three more sections that we need to cover. And so next we're going to be looking at what's called a voltage division rule, and it applies to series circuits. And so we're going to use this rule very often. So it's very important that you become familiar with it and you feel comfortable using it. Before we start using it, we're going to look at what is also called the ratio rule. And it comes from the fact that in a series circuit, the larger the resistance, the larger the voltage across the resistance, right? And this actually comes from Ohm's law, right? Because when you look at Ohm's law, which is the product of the current and the resistance, the voltage is directly proportional to the resistance, right? And so what that means is that if you look at this circuit, for example, right, um, obviously they're in series, so the current through each of those resistors is the same. And from Ohm's law, we know that the current through R1 is V1 over R1. The current through R2 is V2 over R2, and the current through R3 is V3 over R3. Now that comes from, again, from Ohm's law. So if the currents are the same, that means that I1 is equal to I2 is equal to I3, because the current is one single current. And so this is what this is saying. If you have I1R1 will be equal to I2R2, R2V2. Let me repeat that. Since I1 is V1R1 and I2 is V2R2, then that means that V1 times R1 is equal to V2 times R2. And if we solve for the ratio of the voltages, then you get this, right? So that's what that comes from. So it basically says again that V1 divided by V2 is equal to the ratio of the resistances R1 over R2. And that's called the ratio rule. And again, if you don't remember the exact ratios, just go back to that definition of current, right? For both of these resistances, and you know that they're the same. And if you equate both equations from Ohm's law, then you're going to get this. But it's also useful to know because it gives you an idea where you're going with the voltages. For example, it says here, what is the voltage V1 in this circuit? How do you find V1 in this circuit? Okay, well, notice that they're not giving you the source voltage, right? The only thing you know is that the voltage across R2 is 6 volts. They are giving you that. So in this expression, if you look at this expression here, you know R2 is 3 ohms. You know R1 is 6 ohms. And you know V2 is 6 volts, right? So you can solve for V1. So by doing that, you have R1 over R2 is 3. I'm sorry, it's 2. 6 divided into 3 is 2. Times 6, which is this voltage, gives you a V1 of 12 volts, right? And if you have questions, don't worry about it. We're going to be looking at it in the next page. That's where they solve this problem. But I'm just showing you how easy it is to apply. If you want to know what V3 is, right? Well, V3 will be, you can use any of those of the other resistors, right? Because you already know this voltage. So you can equate it to V1 or you can equate it to V2, right? Because this expression will hold the same simply because the current are the same through the resistances. So again, it's easy to find in the first question what V1 is by the ratio. R1 over R2 is equal to 2. 6 into 3 is 2 times this voltage V2 is 6 times 2 gives you 12. And that's what you have here, right? 12 volts. So if you apply the rule again for V3, right, you have, well, for V3 then, same thing. You can say, well, V3 over V2 is equal to R3 over R2, right? Just pick the ratios, right? Or the same thing, V2 over R3 is the same as R2 over R3. It doesn't change the values, right? And again, you're looking for V3, Then all you gotta do is substitute for the value of V2, which is 6 volts, and the ratio of the two resistances, which gives you 1, and that gives you a V3 of 2 volts. So notice how you didn't have to know the value of the source voltage in this case, because we are given one of the voltages, and if you know one of the voltages, you'll know the other ones if you know the resistances. And based on Kirchhoff's law, then when you add up the voltages, right, you know that V1 is 12, right? We found that out. V3 is 2, and V2 is already given at 6. So when you add up all the voltages, you get the source voltage is equal to 20, which is found by using Ohm's law, Kirchhoff's law, sorry, right? By simply adding the voltages. So one thing that is clear is that, as we mentioned at the beginning, that the ratio of the resistive values determine the voltage division in the series circuit. And the greater the resistance, the more voltage you're going to see across it. And you can see this in this example, right? The greater the resistance, the more voltage you have, right? The smaller the resistance, the least voltage you have. Okay. But again, the current remains the same, right? The idea is that the current remains the same. But the impact is that the largest of the series elements will have the most voltage applied to it. Okay. So make sure you understand this relationship here, just to know how this very large voltage will produce a very large, this very large resistance will produce a much greater voltage than V2 or V3. But since in comparison R2 is much greater than R3, V2 will be greater than V3. Okay. So now we basically going to use that rule to come up with a more really important, more useful rule also, that is called voltage division or voltage divider rule, or VDR. This is one of those very important methods that you're going to use to find voltages and other things in series connected circuits. And so, and here we have a very simple two resistors connected in series tied to a source. And so we know that the total resistance is just R1 plus R2, and the source voltage will be equal to the current through R1 will be equal to the current through R2, right? We know that from our previous study with a series resistance, series connector resistors. We also know that if we want to find the source current, we can divide the voltage being supplied by the total resistance, right? So this is this equation here. Excuse me. So if we apply Ohm's law to each of the resistors, to that equation here, V1 we know is I1R1, V2 we know is I2R2. But I1, so we know, is equal to I2 equal to the source current, which you already know is this expression. So if we substitute this ratio into this new equation here, see what you get. You get R1 times the supply voltage over the total resistance, right? And in this case, V2 is R2 times the supply voltage over the total resistance. And this gives us that rule. It's a very useful rule. Now, I don't necessarily like the use of E in this expression, because voltage division applies not only to voltage being divided coming from a source, but also to any voltage that divides can be applied to this rule. So normally I don't like to use that E here, but just keep that in mind, that this applies to any voltage that's being divided, not just to voltage coming out from the source. By being divided, I mean if you apply Ohm's Kirchhoff's law to this figure or to the circuit, you know by KVL that this voltage being supplied is equal to V1 plus V2, right? So that means that the voltage being supplied splits into two voltages, V1 and V2, right? So this voltage splitting into V1 and V2, And what this expression, the voltage division rule, is doing is allowing you to find either of the voltages, as you can see here, without calculating the current. Okay, and that's the real use of this. Notice again that you're finding a voltage X related to a resistance X without knowing or without having to find the current. So in this case, V1 is equal to R1 divided by the total resistance times the voltage, the splits, or the voltage that divides, which in this case is the source voltage. So another way that I like to express this this method is saying the voltage here is equal to the volt or to the resistance that is being calculated next to the voltage you want. So V1, this will be the resistance next to that V1, is equal to V1 divided by the sum of the two, R1 plus R2, times the voltage that splits. R1 plus R2, because that's the total resistance, right? It's the same thing. And you'll see you need to practice really to really grasp it and to make a lot of make more useful how you use it. But so we'll do some examples. So in here it says, for instance, it says in this example 516, without making any calculations, how much larger would you expect the voltage across R2 to be compared to the voltage across R1, right? So the voltage across R2 is seeing a resistance of 60 ohms, and the voltage across R1 is seeing a resistance of 20 ohms. So R2 is 3 times the resistance of R1. So you would expect that the voltage will also be about 3 times that of V1, and because it's directly related to that. And then we're going to use V1, this voltage here, by simply using voltage division. Okay, so right, so it's just a simple series connected resistance to a battery. So like we said before, since the resistor R2 is 3 times R1, we expect V2 to be at least, or to be 3 times V1. Okay, R2 is 3 times V1 R1, so V2 is going to be 3 times V1. Now they say, well, find the voltage V1. So if we use the rule here, look at the rule, right? The equation. We're saying that this voltage V1, and this is one way you can read that that technique, is that a rule that the V1 is going to be equal to the resistance adjacent or next to the voltage you're looking for. The resistance next to the one you're looking for is 20. So it's going to be equal to 20 divided by the sum of the resistors, R1 plus R2, times the voltage that splits. Because remember, this is the voltage that's splitting among V1 or between V1 and V2. Because you know, again, remember by KVL, this voltage 64 is equal to V1 plus V2. So again, V1 will be equal to the resistance next to the voltage you're looking for, 20, divided by the sum, 80, times voltage that splits, 64. So 20 over 80 times 64. And that's what you have here. 20 over 80 times 64. See? It gives you 16 volts. All right, so make sure you practice that. Make sure you understand that, what I just described, and using this equation. Okay? This voltage is 20 over the sum, 20 over 80 times the voltage that split. Well, what is V2? V2 will then be, if we apply the same rule, it'll be 60 divided by the sum, which is 80 times 64. 60 divided by the sum, 80 times 64. Right? So it's again 60 divided by 80 times 64 gives you 48 volts. Okay? And we also knew that because remember we said at the beginning how much larger is V2 compared to V1. So V2 is going to be 3 times V1. So you could have also found V2 based on that expression or that knowledge, and it should get the same result, 48 volts in either case. And by KVL, we should get the same result, because when you add those two together, 16 by plus 48, you get 64, right? So these little equations here are very important. This things that we pointed out here are very, very important for you to really grasp and understand. This expression YV2 is 3 times V1. How do we get this voltage V1? Based on the voltage division rule, and why this corroborates what we already know from KVL. Okay, so this is a very useful example. Let's do another one. We're going to use the voltage division rule to find V1. Now, again, notice what is it that we know in this circuit. Okay, the things that we know are the resistances and the voltage being supplied. So I got everything I need to find V1, actually, because if you look at the equation again, what I need to find V1 will be R1, the total resistance, and the voltage being supplied, right? And I have all that in that circuit. So the total resistance, again, will be 2 plus 5 plus 8, right? The voltage being divided is 45, so I have 45 times 2, which is the resistance next to the voltage I'm looking for. 2 times 45 divided by 15. See? And we can do the same thing for V3. V3 will be the resistance adjacent or next to the voltage I'm looking for, divided by the sum of all the resistances. Right? In this case, we have 3. So it'll be 8 divided by 15, which is the sum, times 45. And then you got 24. Okay. Notice again that we don't know what V2 is, but we can easily find it. We can find it again by reapplying voltage division, and I'm going to leave that as an exercise for you. Find again by just using voltage division. But you already know by KVL that 45 is equal to this V1 plus this voltage plus V3. You know V1, you know V3, you know the total voltage, so you can solve for V2, right? So try to find it both ways, by KVL and by using voltage division. Okay. So that's how you know that you can extend the voltage division rule to any number of resistors, not just to 2. Okay. Let's look at another example. It says find the voltage V prime, and hopefully you did the previous exercise I recommended to find V2, so you get a little more practice. But in this case, they're asking us to find the voltage V prime. The voltage V prime is the voltage not just across V1 or just across R2 rather, but is the voltage looking from R1, R2, is across these 2 resistors. Okay, so if you put a meter from the top of R1 to the bottom of R2, you'll be looking at V prime. That's what they want to know. Well, we can reapply that rule again, because then you say, well, the voltage that I'm looking for is across those 2 resistors. So it'll be the resistors that you're looking right across that voltage, which in that case will be 7 divided by the total resistance times 45. And that's what you got right here. 7 divided by the total resistance times 45. Okay? And that's what is useful about this rule, that you can apply it in many different ways. And in all the cases, we didn't have to find the current. That's the actual benefit of using this rule. You don't have to find the current. Notice that. All right, let's do one more. So let's go 520. It says design the voltage divided circuit in figure 540 so that the voltage across R1 is 4 times the voltage across R2. So we want the voltage across R1 to be 4 times the voltage across R2. Okay, so the total resistance again is going to be the sum of the two resistors. We want VR1 equal to 4R2, so that means that R1 is going to be equal to 4R2. Remember that voltage ratio rule, right? It's always the case. So the total resistance, again, using this expression, we can substitute for R1 equal 4R2 here. So the total resistance is then 5 times R2. Okay? And if we apply Ohm's law, we can see that the total resistance, right? Since by Ohm's law, the total resistance is equal to the this voltage divided by the source current, right? Then we know what this voltage is. We know what the current is. So if we divide by the voltage over the current, we get a total resistance of 5 kilo ohms. Okay. And so now that we know the total resistance, and given this expression here, the total resistance is 5 times R2, you can solve for R2. Since we already solved for R2, then you can solve for R1, right? Okay. So make sure you practice this rule. The best way to really get familiar with it is to practice it and to really become comfortable using it, because later in the next chapter we're going to be using another rule that applies to current, and they look very similar but they're very different. But if you're not comfortable using one or using either one, you're going to get you may have some trouble going forward. So it's very important that you feel comfortable using it. So I would recommend you redo these examples without looking at the solutions. Don't look at the solutions. Just redo the examples, what they're looking for, get them on your own, and then look at the solutions. Okay? All right. So now we look at what happens in a series circuit. Some of the things that we can do is what is called the interchange of series elements. What that means is that in a series connected circuit, I can interchange elements any way I want as long as the connections remain in series. Now, for instance, if I change the position of the resistors, if I exchange R2 and R3, right? The overall behavior of the circuit doesn't change. What that means is that if I exchange the position of R2 and R3, and you can see this in these two circuits, the total current doesn't change. The total resistance doesn't change. The total voltage being supplied doesn't change, does it? It doesn't, right? It doesn't change. Whether I have it like this or like this, it doesn't change the overall behavior of the circuit. However, what changes is what is it that I'm looking for. If what I'm interested is in this resistance R2, and this is the one I'm observing. If I swap it, then I will no longer be looking at R2 when I swap it. I'll be looking at R3, right? If I stay in the same place. If my meter stays here, it's going to change that. So that changes, right? But in the overall picture, the overall behavior of the circuit doesn't change. The individual voltages will change, and the resistances will change when you swap elements like that. And sometimes it makes it easier to work with circuits by having that ability, by swapping elements like that. And you can do the same thing with R1 and swap any to R2. And you can even move the battery over this side, and it's not going to change how the overall circuit behaves. Example, let's look at this circuit here, and it says find the current I and the voltage across the 7 ohm resistance. Okay, and what they've done here, now remember, you don't have to do this. This is just another way, another tool that you have to find what you're looking for, because there's other ways you can do this, right? You can apply KVL and work your way around that, but let's just use this technique so we can really just what we're doing is just simplifying the circuit. So they want to know the current, right? So but there's two sources. So what we're going to do is, in order to see more easily what's going on, they're going to swap the position. They're actually just swapping the position of the 4 ohm resistance and the 12.5 volt source, swapping from each other. And if you swap them, right, see, you get this circuit, right? Because now you're putting the 4 ohm in front of the negative of the voltage source, right? And by doing that, you're joining the positive and the positive of the 2 voltage sources. Now notice that it's still a series connected circuit, right? That's the important thing. You're not changing the overall behavior of the circuit by doing that, okay? And notice again that it's important that you keep the connections consistent, right? Because if you look here, this positive, when you swap it, right, you gotta keep the positive in the same place as far as the polarity is concerned, right? You can't just swap it and flip it, because if you flip it, then you have the negative on that side, and that's a whole different circuit, or a whole different result rather. So it's important that you keep polarities consistent. Now resistance doesn't matter because resistors don't have polarity, okay? But in the case of batteries, it's important that you keep the polarity. So that's what we did here. We just swap the 12.5 volt by the 4 ohms resistance and come up with this circuit, see? And by doing this, now you can combine these two batteries into one battery, right? Because now they're subtracting from each other, right? Remember by KVL, right? This will be 50 minus 12.5, right? It'll be a voltage rise or voltage gain of 50 minus a voltage drop with 12.5, which gives you a really net voltage of 37.5 volts. Okay, so this circuit here in figure 543 reduced to this circuit here now in 544. And that was a lot easier to find the current, right? Because now the current is just equal to this voltage divided by the total resistance. So 37.5 divided by 15, 7 plus 8. And if you then want to find the voltage across the 7 ohm resistance, again, it's just the current times the resistance, right? So very easy. By the way, I'll leave it as an exercise for you in this circuit. Find this voltage here using voltage division. So instead of using Ohm's law, find the voltage using voltage division. Apply that rule to find it. And you should get the same value. Okay? And you see how easy it is, right? So try that as an exercise. Now we're going to talk about notation. It's important that we talk about notation when we're referring to voltages and we're referring to ground in a circuit, because it keeps everything consistent. Ground in our terminology, again, this is the symbol for ground, is normally considered to be 0 volts. Now, that's just a convenience of defining ground, but ground doesn't always have to be 0 volts. We just, always define it as 0 volts, but it could be some other number. Okay, it doesn't have to be 0 all the time, but in general, we decide that is 0 volts. Sometimes we indicate that ground may be different, but for most practical purposes, we define it as 0. In this circuits here, if you look at the circuits, we can, based on the ground symbol, we can draw the circuits in these 3 ways, and they still represent the same circuit, right? Right. A lot of times we draw circuits like this, schematics, just to make it look nice, but you can draw it really any way you want, any way you feel comfortable with the circuit, as far as you don't change the actual circuit itself. Notice that here, in these 3 cases, the circuits look slightly different, but the actual circuit, nature of the circuit didn't change. You still have a battery connected in series with 2 resistances in any one of those circuits. So So replacing, if we use the notation here, right? If we replace the special notation for a DC voltage with just a standard symbol, we can do this. In other words, another way of representing voltages here, you see, or voltage sources, is by just having this symbol here, okay? Just that little circle, okay? And in this case, what this represents is, it just simply represents that R1 and R2 are directly connected to that source, see? It's just a shorthand notation or a shorthand representation of sources. So again, make sure you're understanding that this drawing of this battery here and this drawing of this battery here are the exact same thing. What this is obvious again, because this is what we've been using so far, saying that R1, and if you follow the circuit, right, you can't go wrong. That's why it's important that you follow the circuit, just like you do in the lab. If you follow the path, in this case, R1, if you follow that connection, R1 is connected to the positive of the source, isn't it? And the negative of the source is connected to ground, right? Well, if you look on the left-hand side way of drawing the circuit, we're doing the same thing. It's saying R1 is connected to the positive of the source, see? The positive of the source. They don't show you the other side of the battery because it's understood that the other side of the battery is going to be connected to ground. But in this notation, that's how we use it. In this notation, it says that the positive of the R1 is connected to the positive of the source. All right, so make sure you understand that notation. Same thing here. See, in this notation, in this circuit, if you look at the circuit in figure B, right, again, this is obviously what we've been doing so far. You have a resistance connected to R1 and R2 connected together. And R1 is the one connected to the negative of the voltage source, right? It's connected to the negative of the voltage source. It's obvious from this connection. You can't go wrong by following that. And then the positive is connected to ground. Right? The drawing is telling me that. So in this notation, if I follow this notation, as I did in the previous example, you can use this because it tells me that R1 is connected to the negative 5 volts, see? Negative. All right? So this is a shorthand way of drawing this circuit this way. It's just a shorthand. Okay. Again, this tells me here, if I look at the left-hand side circuit, that where, as far as R1 being connected to the negative of the 5-volt source, there's another connection here that is not showing, that is connecting the positive of the source to ground. So it's not shown here, but it is implied. That's the part I want you to understand. It's implied because these two are equivalent. Okay. All right. This is also another good example. It's telling me here that between R1 and R2, there's a source being connected. See, there's a source connected to a 25-volt source. So how do I know that? I know then this point will be connected to the positive of this battery, and the other side of the battery will go to ground. See, it's just a notation. It's a different way of drawing circuits. It's a shorthand way. A lot of times it makes things easier to draw and not so crowded because you don't have to be keeping tracks of all the batteries like this all the time. It's just a shorthand way. Okay. All right. The other thing we're going to be looking at is what we call double subscript notation. And this is what we have voltages, and we want to make sure that, basically we want to make sure that we know the signs associated with each side of the connection, right? And for example, if you look at the circuit A, you have a voltage AB across a resistance R. And based on our convention for current, we know that the current is going from A to B, right, towards the lower potential. Well, so then we know that A is the more positive side of the potential, and B is the negative side, right? or the lower side in the potential. There's a voltage drop here, in other words. Same thing here, right? If we follow the notation and direction of current flow, we know the current is going from B towards A. So if you were to put a meter from A to B, positive in A and negative in B, you'll get a negative voltage, right? Because you'll be measuring a negative voltage. By keeping the leads of a meter, the positive in A, the negative in B will give you a positive voltage, right? In this same example, in this other example here, same idea. If we keep the meter in A, a positive lead in A, and the negative lead in B, you read a negative voltage, and you've done that in the lab, right? When you swap the leads. So we've done this before, but we're just pointing out the meaning of the double subscript notation. So if we notice in these two circuits, in these two simple circuits, that we can then associate, there's two literals associated with the voltage A and B, right, with each of the nodes. And the letters doesn't matter. It could be X, Y, or 1, 2. It doesn't matter as long as you know which one is which, right? For instance, when we do measure voltages in the lab, we don't label A or B, right? We just measure it because we know what we're looking at. So AB could be X, Y, could be 1, 2, whatever. So in any case, but if we use the same example as in this figure, then the double subscript notation VAB means that point A is at a higher potential than point B. Okay, so in this double subscript notation, the first literal or the first letter that you see tells you that is the higher potential point or the more positive point on that voltage, and the second literal tells you is the more negative point, right? So another way of saying that is that the voltage AB is the voltage at point A with respect to point B. Okay? So those are two very important ways of understanding the notation here. Again, when you look at a voltage like AB, it means that A is at the higher potential than B. Okay? And if you look at, or saying that A, the voltage AB at point A with respect to point B is the same thing. Okay, so that's the double subscript notation. Always remember that the first literal indicates the higher potential, right? And the second literal indicates the lower potential, or in this example. We also have another notation that's called single subscript notation, and it's really the same thing. It's just a special case, because if you look at this double subscript notation, but it just happens that B is grounded. If we make B the ground, we then call that single subscript notation. Okay? Because in single subscript notation, like if we look at this circuit here, right? Let's look at the double subscript notation as we explained it before. So we have AB, right, will be the voltage from A to B, or the voltage A with respect to B, AB, right? You can do the same thing here. If you look at A to ground, right, A to ground, we haven't labeled ground, but we could label it. It could be labeled, it's fine. Let's say that we label it C, right? We label ground C. So VAC will be the voltage from A to C, or from A to ground. VBC will be the voltage from B to ground, right? So what this notation is saying is that since ground doesn't change in a specific circuit, we can just not label it, because we know it's ground. We know it's all in this, for most practical purposes, it's going to be 0. So in this notation, we just use one literal. Okay. So again, if you look at in this example, we'll have the VB is 4 volts from B to ground. VA is 10 volts from A to ground. But notice that if I write VA, it's only using one subscript. So if I look at a voltage that only has one subscript, I have to understand that it's referring to ground. Okay? So the single subscript VA notation indicates the voltage at point A with respect to ground. If the voltage is less than 0 volts, then you have a negative voltage associated with it, right? Just like, you know, the previous case. All right. Let's see this one. This is another example here. In this case, if we use the notation that we used previously in drawing circuits, we can redraw this circuit. Look at this circuit here in figure 551, and look at this figure here in 552. They're exactly the same circuits, right? Other than, you know, if we know the voltage tied to it, right? In this case, we'll say, well, this voltage VV is tied to a 20 volt source, and this voltage VA is tied to a 16 volt source in the positive side, both of them. Okay, and we're going to see in the examples in more detail. Another useful relationship to understand is that when we look at this notation AB, it's also indicating the difference between those 2 points, A and B. So if you look back at this notation, AB, right, what you're doing is you're really looking at the difference in potential between A and B, right? So if you look, for example, at this circuit, right, if I want to know what VAB is really the difference between A and B, this expression right here, right? In other words, if the voltage at point A and B is known with respect to ground, then I can find VAB by using just the difference of the two, right? Because I know the voltage in this case at this point is 10, and the voltage at this point is 4. So the difference between them is 6 volts. So that the voltage across this 6 ohm resistance is 6 volts. See? All right, make sure you understand that. All right, it's like being in 2 different points in a hill, in 2 hills, right? This hill is at 100 feet, and this hill is at 80 feet, right? So the difference between the 2 points, it's going to be what? 100 minus 80, right? 20 feet. It's the same idea. So there's a difference in voltage between those 2. All right, let's look at example 552. And from that it says, find the voltage VAB. Well, it's what we said just now. The voltage at A is 16. The voltage at B is tied to 20. So the difference between the 2 is A, because they won the voltage AB, right? So that's what's important, that we understand the notation, meaning that we're going to subtract from A minus B. Okay, so in this case, VA is 16, VV is 20, so it gives us a voltage of -4 volts, right, across this resistance. Okay, so that's what's important, that you keep the notation. Okay, so that means that the negative indicates that the voltage at B is at a higher potential than the voltage at A, and you can see that from here, right? This voltage is a higher potential than A. All right, let's look at another example. This one will be this figure in this example here. And we want to know the voltage A. And in this one, we're given the voltage at B. So this is the voltage with respect to ground. And this voltage AB is the voltage from A to B, or from A with respect to B. So to find the voltage with for A with respect to ground, I can apply the same equation here, right? So in this case, I know this voltage, and I know this voltage. So all I do is solve for this unknown voltage VA, and if I do that, I get 9 volts. Okay. All right. What else? Let's look at one more. This is 524. Looking at this figure, it says, what is the voltage AB in this example? Well, again, the voltage AB is going to be 20 minus 15, right? It's always important that you take the sign into account. So 20 minus 15 gives you 35 volts, okay? So that's what this indicates, okay? All right. So more examples of the same. I'm just gonna leave you to look at that one, 525. But let's look at 526. It says in figure 559, which is this one, right? It says find the voltage VAB, right, which is indicated right here across R2. Find the voltage CB, which is the voltage from across the R1 resistance, and the voltage VC in this network, right? VC is right here, right? Now, before we do that, let's study this a little, just a little bit, right, and see what's going on. Well, what you see is that you have a series connected circuit, 2 resistors, and it's showing you just the shortcut way of drawing the circuit, because it says that A is connected to the positive of a 35 volt source, and C is connected to the negative of a 19 volt source. Okay, so there's really nothing new here, right? It's just the notation is a little different and the way we draw in the circuit, but we really have a series connected circuit. So there are a couple of ways we can look at this problem. The first one is to look at the diagram like in this figure 560, right? And we notice that there's a 54 volt drop across the 2 resistors, right? In other words, you go from 35 volts here to minus 19 volts here, right? So that means that we drop 35 down to minus 19 is a total distance, if you will, of 54 volts. You notice that, right? Because you got to go down to 0 and down into the negative realm into minus 19. So the total difference, the total distance, if you will, from 35 to minus 19 is 54 volts. And ground is somewhere there, right? So, so the current can be found using Ohm's law. And the voltage levels can be found then using Ohm's law as well. So the current is then, again, it's a series connected circuit. So you really have a total voltage across the 2 resistors. The voltage that, in other words, if you were to put a meter from A to C, if you put the meter across A and C, you will measure a voltage at that point between the two, these 2 points, right? But the current is the same, right? And if you were to measure that voltage, you will measure 54 volts, right? Because one side is connected to the 35 volts and the other one is connected to the minus 19 volts. But again, the total voltage is 54. So the voltage across the 2 resistors is 54 volts. So dividing that by the sum of the 2 resistances gives you the current, see? And if we apply Ohm's law, then it's very easy to find VAB, which will just be that current times 25 ohms, and VCB, which is the current times 20 ohms. Now, notice one thing, that they want VCB. So in other words, if you were to measure that voltage using a meter, you will put the positive lead at C and the negative lead at B, because that's what the literals indicate, that the more positive connection, or the more positive voltage, the higher voltage is at C. So if you put a meter there, it'll read a negative voltage, right? You understand that? So you will read then minus 24 volts, okay, for that reason. Now, if they were asking you for the voltage BC, that voltage will be positive. But since they're asking you for the voltage CB, they're swapping the literals, then the voltage will be negative. And then the last thing they want is saying, what is the voltage at C? Well, the voltage at C is just C with respect to ground. And as you can see here, it's just, this C node is just tied to the negative of the voltage source. Okay, so this is just notation. I'm going to leave you with maybe you can do the other examples for practice. Let's do one more. Let's do this one, 527. It says, use the voltage division rule to find the voltages V1 and V2 in this figure, right? Again, study the figure, right? Notice that this R1 is connected to the positive of the 24-volt source, and this R2 is connected to simply to ground on that side. But it's also connected to V2 on the other side, okay, to the positive of V2, because that's what this indicates. So if we use Ohm's law, right, then you can say, well, the voltage 24 volts is the one that's splitting between R1 and R2. So 24 is equal to V1 plus V2, right, because that's what we time, right? And you notice that is really this same circuit on the right-hand side, right? Maybe that makes it a little more obvious, right, what this is. The voltage 24 is just connected across R1 and R2. But it's important that you understand this drawing on the left as being the same as this drawing on the right. So knowing that, then you can simply apply Ohm's law, voltage division rather, and say, well, V1 is equal to R1 divided by the sum times 24. So R1 divided by the sum times 24. R2, or V2 rather, is R2, or 2, divided by the sum, 6, times 24, or 8 volts. Okay? So again, it's just the notation is important, and the way of drawing the circuit. The last thing we're going to talk about is the ground connection. Remember, the placement of the ground doesn't really affect the magnitude or the polarity of the voltage across any of the elements. It's just a matter of convenience where the ground is connected. And so the ground is not always connected at the bottom of a circuit, for example. Right? And in all these examples we'll be doing so far, we're getting into the habit of connecting the ground at the bottom. But that's just a drawing. In the real world, this ground could be in any point in any direction, and so we need to be aware of that. And this is what this is showing here. So in this case, it's important that we pay attention to where the ground is. So for this example, VA, if you want to know what VA is, and if we use follow the notation we used before, we're looking for A to ground, right? So from A to ground, it's just 16 volts. You can see that, right? From A to ground, because ground is now here. Okay? It's not at the bottom anymore. It's here. So from A to ground, it's just 16 volts. If we want to know what VB is, now VB is here. Look at this, rather, node B is here. But the voltage VB indicates the voltage from B to ground. So I will have to look at, if you put a meter, you will be putting the positive lead on B and the negative lead in ground, at the ground point. So you're really measuring from this point B to ground. That's what this VB indicates, right? So as you notice here, when you go from B to ground, you're really adding 2 voltages of the same polarity, so you have a total of 16 volts. See? So this voltage B with respect to ground is 16 volts. Okay. What else? Okay, so now they're going to know what VAB is. Well, VAB can be found by looking at the difference, between the voltage at A minus the voltage at B. We already calculated those two, right? The voltage at A is 16, the voltage at B is 16. If we subtract those two, is 0. And so we kind of know that already, right? Because of how the circuit is. That's what you will be measuring. You can also do a KVL, right, around the circuit, and you're gonna get a VAB of 0. And you can also redraw this any way you want to make it look a little different, and you should still get the same results. Okay, so that's what that is. I'm going to do one more for you before I leave this chapter, and that's all we're going to cover in this chapter. In this example, in this figure, for this circuit, we have voltage source of 240 volts and another voltage source of 60 volts connected to 3 resistors in series, right? It's a series connected circuit, but look at where the ground is, right? The ground is here at A. So we need to be just paying attention to that. So now it says find the voltages VA. So VA with respect to ground is just ground. This is the ground point, right? How will you measure that? Well, if you really need to do it, right? Although it's obvious that what the value is, you will put both leads at A, right? Because you're measuring at A. So I'll give you 0 volts, right? And the voltage B, where is B? Here. B with respect to ground. So it will be, again, imagine putting a meter, one lead at B and the other one at A, right? Look at what you'll be measuring, right? You'll be measuring the voltage from here to here. Or you can go the other way, right? You can go in this direction and move the leads from one lead here and the other one lead here, right? So you're really measuring either this portion or that portion of the circuit. It won't make a difference for the value of what B is in C. So let's find those values, right? So from this circuit point of view, I can find the total current, right? It's not going to change how I found the total current. But now I can either use Ohm's Kirchhoff's law, or I can combine these two values of battery together, right, into one. And as you can see here, they're connected. The polarities are going to subtract, right? Because if you go from this point to that point, you have a voltage drop. But if you keep going, then you have a voltage gain of 240 volts. So in essence, what you have is if you combine those two voltages sources, you have 240 minus 60 as one single source, divided by the total resistances, or the total resistance gives you this expression, which gives you the total current, right? And based on that, then the rest is easy, because then you can find V2, you can find V1, you can find V3, right? And then VB will just be this voltage minus V2 minus V3, right? And VC, which is this, where's C? C, here, right? It's just the voltage from C to ground, right? Because we're looking for C to ground will be minus V2. Notice that, right? Always remember when you put you can think of putting a meter, and when you put the leads in those meters for the meters. Okay. And finally, VAD, if they want to know what AD is, so they want to know what this voltage from A to D, right? We know this one, right? We already found V1. Where's V1? Or we can find V1, because V1 is just the current times R1, right? But in essence, what you have is that VA to A to D, right? Because now you're going from A to D, right? Will be the difference between this voltage source and this voltage drop right here. And again, knowing what V1 is, then you just subtract the two voltages and you get 222 volts. The good thing about this is, as an example that I will urge you to practice, and again to find these solutions or this answers without looking at the solutions first. Just do it on your own. Copy this circuit somewhere on the page and try to find them. Try to find what they're looking for. And what you'll find also is that you'll see that there's more than one way to find that answer. And that's what I want you to start really learning this, because the solution you see here is one possible solution. There might be other solutions. And it's important that you start looking into the different ways of finding the different ways that you can find the solutions, okay? So we'll see you in the next chapter.